to the research session 15, Data Mining 2. I'm Wang Chen Li from Penn State. I am the session chair for today's presentation. This session will run for 90 minutes. Okay. Please note that we are recording the session and we'll make the recording available after the meeting. During the presentation, if you have questions, please use the chat feature to send them to me, and this will be used for question and answer at the end. Please also keep yourself on the mute mode throughout the presentation, and be sure that your video setting is unchecked. The spotlight my video when I speak this option. Please uncheck that. Okay. Okay, so let's start our session. We have 5 presentations today. The first talk is on multi-scale frequent co-movement pattern mining. The speaker is Shihab Ahami. He is a PhD candidate at the Department of Computer Science and Engineering from University of Colorado, Denver. His research focus including data management and mining, with a special interest in mining multivariate spatial temporal patterns from trajectory datasets. Let's welcome Shihab. Shihab, do you want to talk?
Hello, everyone. The video would be better.
Okay, go ahead, please.
Hello, everyone. My name is Shihab, and I'm going to present my paper on multi-scale frequent co-movement pattern mining. So first, let's talk about what are co-movement patterns. So basically, there are movements of multiple objects that happen at the same time, but those objects do not need to be close to each other, and also their movements can have different shapes. So for example, here we have a soccer field where players are moving around the field. And here we have a person who is walking, and we can consider each joint as a moving object. But why are we interested in frequent co-movement patterns? And the reason is that if a pattern happens more often, probably it can give us more information about the objects and their interactions. So in the soccer example, if we mine frequent co-movement patterns, probably we can find the overall strategy of the team. Here, we have the related work, and the red cells basically shows that they're different with our work. So in the first group, we know the shape of the pattern beforehand. So basically it's a query processing problem, not a mining problem. And in the second group, we don't know shape of the pattern beforehand, so we have to mine them. However, they assume that the objects are going to be close to each other. That reduces search space. And also they don't look for frequent pattern. In the next group, they basically look for frequent patterns, but they assume that objects are close to each other. And in the last group, there are solutions for mining frequent sequences from symbolic time series, so they are not spatial. So here we can see a formal definition of a co-movement pattern. Each element basically shows one or more spatial features, such as direction and displacement. However, in this paper, we only use direction. And each row of this matrix shows a movement pattern for a single object. So here we have a co-movement pattern for 2 objects. And the object 1 goes up and then to the right, and object 2 keep going to the right. And it happened 5 times, so we say the support of this pattern is 5. So we call a co-movement pattern a frequent pattern if it happens more than a given minimum support threshold. And that's depend on different applications. And maximum window size is basically shows the maximum temporal length of the pattern. So for example, in soccer, patterns are just a few seconds short, and we don't want to mine patterns that are longer than that. So given a trajectory data set, a minimum support threshold, and a maximum window size, our goal is to mine all frequent co-movement patterns from that data set. However, this is very challenging because if we have a small data set that has only 10 objects and the maximum window size is 10, and each trajectory has 100 data points, there are going to be more than 100 million possible co-movements in that data set. And if you increase the number of objects to 20, there are going to be more than 16 billion possible co-movements. So the solution that I'm going to explain in the next slides, basically we're going to reduce this number. Our solution are going to have 3 steps. I'm going to go through them one by one. Here's our baseline solution. So we assume that each iteration has 2 main steps. In the first step, we first find frequent movement patterns for single objects. And then in the second step, we just join them to generate a frequent co-movement patterns. So here's an example. In the first iteration, let's say we found these 2 movement patterns for object 2 and object 3. And then in the second step, we join them to get this frequent co-movement pattern. In the next step, we do the same thing again. We look for longer movement patterns. And again, in the second step, we join them to get this new co-movement pattern. So first, I'm going to talk about the first step, finding movement patterns, and then I will move to finding co-movement patterns. So the first improvement we are going to apply on this. So in each iteration, instead of generating movement patterns from the scratch, I'm just going to get the patterns that I had in the previous iteration and just extend them. For doing this, basically we can use the API property. So we look for joinable patterns that are basically patterns that are the same except the beginning and the end, and join them to get the new pattern. However, to find the joinable patterns, we have to compare all patterns against each other, which gives us this polynomial complexity, and it's going to take a long time because there are many movement patterns at each iteration. To improve that, we can actually have pointers from each occurrence to the trajectory. So here we have a pattern that happened 3 times. For each of those 3 times, we can go back to the trajectory and see what happened next. And we can see in 2 of them, object moved right after this, and in 1 of them, it moved up. So simply, we can extend the pattern and get the support, which gives us this nice linear complexity. And in a more complex version, we can assume that patterns do not have to be exactly the same, so we can allow temporal gaps in the middle or in some part of that, and we assume it's still the same pattern. And it's going to be obviously more complex because there are going to be more possible candidates, and also there are different measures to compute the support. And after we did a literature survey, we found this head frequency measure is the best for a problem. However, the issue with that is it's not monotonic, basically meaning that we cannot do the extension strategy explained in the previous slide, and we have to, at each iteration, we have to generate all the patterns from the scratch. So to make it more efficient, we came up with this recursive algorithm that basically before generating the patterns, it gets rid of elements or directions that are gonna give us duplicate patterns and gets rid of that. And you can see the details about this algorithm in our paper. Now we're done with the first step. So we assume we have the frequent movement patterns. And now we're going to look at how we can improve the joining process for co-movement patterns. So basically, again, the naive solution would be just to combine, generate all the possible combination of those movements, which is going to give us this very exponential complexity, and it's not going to be feasible. So to improve that, we can use a API property, and we can find co-movement patterns that are joinable, that are basically different only in one movement, like these 2, and we can just join them. However, again, we need to compare all co-movement patterns against each other to see which ones are joinable, which is going to give us this polynomial complexity, which is better than the naive, but it still can take a long time. So to improve that, first, we assign our patterns to buckets. So for example, in first bucket, it has all the co-movements that have object 2, 3, and 4. And instead of looking for joinable co-movement patterns, we look for joinable buckets. So here, we know that if 2 buckets are joinable, 2 of these 3 objects must be the same. So I go ahead and generate all this 2 subset of this object set, and I add the bucket ID to them. And I keep doing that for all the buckets. And at the end, it's going to tell me, okay, bucket 1 and bucket 2 are joinable. And I did not do any direct comparison. And now that we know these 2 buckets are joinable, we know they share object 2 and object 3. So for their patterns to be joinable, they have to have the same subpattern for object 2 and object 3. So I use the same technique for each pattern. I generate the subset for object 2 and object 3 and add the pattern ID. And again, at the end, it's going to tell me pattern 1 and pattern 3 are joinable. And I didn't do any direct comparison. So this is going to bring our complexity down to linear, and basically this P of k shows the number of buckets in the kth iteration, and this shows the average number of patterns in each bucket. And the last improvement we are going to do, so in each iteration, instead of joining the patterns again to generate co-movement patterns, I'm going to use the patterns I had in the previous iteration. I'm just going to extend them using the new movement patterns. So here's an example. Let's say these are my co-movement patterns, and then in the next iteration, I get this extended movement pattern. So for object 2, you can for pattern 1, you can see each of these movements got extended in the next iteration. So to generate the new co-movement patterns, I can basically replace these with these extended versions. And for pattern 2, it cannot be extended because the pattern for object 4 does not exist in the list. So we can just discard that. So putting all together, for the first iteration, we need to generate all co-movement patterns. And then for the next iterations, we can just extend them using this strategy. And as you can see, it improves a lot over the naive and the basic solutions. So far, I was talking about mining frequent co-movement patterns in a single scale. Now we're going to do it in multiple scales. So here we have a movement pattern with support of 5. And if it's a soccer field, although all of these movements look the same, but probably they have different meanings. So for example, these 3 can be offensive movements, these 2 can be defensive. So to be able to distinguish them from each other, we define a scale. So we assume movements to be part of the same pattern if they're density reachable. So as you can see, this one in the bottom and this one at the top are both reachable to the one in the middle. So we say all of these 3 movements are part of the same pattern. However, these 2 are not reachable, so we say they're a different pattern. So we can get three new patterns in the new scale, and 2 of them have support of 1 and 1 of them has support of 3. So if minimum support threshold is 2, we can get rid of the infrequent ones. However, in most real-world applications, probably want to do it in multiple scales at the same time, because as you can see, we can get totally different patterns on each scale. So let's say we want to also mine patterns in a smaller scale, and we already know that these 2 patterns are not going to be reachable to each other or to these patterns because they were not reachable in the bigger scale. So instead of computing complexity or reachability for these patterns, I can directly apply the new scale on the right figure. So as you can see, we can use the same technique. These 2 are not reachable, but these 2 movements are. So we can get 2 new movement patterns, and one of them is not frequent, so we can just get rid of that. And I'm just going to emphasize that the scale applies only on movements. So in our co-movements, we can still have objects that are far from each other. And for experiments, we use 2 real data sets. The soccer data set was captured during a 90-minute game, and we excluded the data for goalkeeper because he was not moving that much. So it has 10 objects. And in the gate data set, we asked 100 people to walk 30 times in front of the Kinect camera, and we recorded the movement of their joints at 1 Hertz. And as the evaluation metric, we used the execution time, the memory it took, and the number of patterns that it generated. And for coming up with the default values for each parameter, we just did a grid search. And I'm going to present just a few results because we don't have enough time, but please check our paper for more results. And in all the charts you're going to see, we use a logarithmic scale for the values on the y-axis. So first, we compared our algorithm with the pi plus algorithm, and which is an efficient algorithm for mining frequent episodes or sequences, basically. And as you can see in the soccer data set, as soon as I added the 4th object, it didn't finish in more than 12 hours, so just stop that. And I continued my experiments with 2 and 3 objects. And in this experiment, I increased the maximum window size, and as you can see, our solution worked a lot faster. However, the pi plus algorithm took less memory. In here, the black bar basically shows the number of co-movement patterns that the naive solution would generate, and the red bar shows the number of co-movements that our solution generated. And the blue bar are the number of frequent co-movement patterns. So as you can see, our algorithm did a great job in pruning. And here we can see the execution time and memory. So for this small support of 3, which basically makes almost everyone frequent, it finished in less than 2 minutes, and it didn't take more than 3 gigabytes of RAM, which is great. And here we might pattern in multiple scales. And the black bar basically shows the time that it took for us to generate the pattern in each scale separately. However, the blue one shows, the green one shows the time when we use the strategy I explained before. So for each scale, we derive patterns directly from the larger scale. And as you can see, it made a huge difference. So as a conclusion, we defined covalent patterns for the first time, and then we evaluated our solution with 2 real data sets, which reduced the number of generated covalent patterns up to 50,000 times for the soccer data set and even more for the gate data set. So here in this chart, each cell basically shows the percentage of frequent covalent patterns that included both of the corresponding joints. So for example, here joint 4 and joint 1 for subject 1. And basically we did it for all subjects. And as you can see, this distribution is very different for each different object. So we came up with the hypothesis that we can use these frequent covalent patterns for classification purposes. And if you want to download these slides, you can just scan this QR code right here. Thank you so much.
Okay, thank you for the nice presentation. Okay, Shihab, can you turn on the unmute so you can answer the questions from the audience? I have a question. I see a question from KZ Tony. Here it says that the algorithm seems to be similar to subsequence pattern mining, and the data structure similar to prefix scan algorithm by Jian Pei and Jiawei Han. If I'm not wrong, what is your comment about that?
Can you hear me?
Okay, it's Karen. Yeah. Yes, please.
So yes, it's kind of similar to subsequence pattern mining, but I think there are 2 main differences. The first one is that our work is spatial. So basically all of those reachability concepts, they do not apply on that algorithm. And the second one, I think that work applies only on one sequence. Our work was applied on multi-sequences.
Okay. Okay. Is there any other questions? Okay. I myself has a question regarding to the data and the assumption that been made. Okay. So I'm wondering whether what is the requirement for data? This is trajectory data, and I'm wondering whether is the time and the timestamp or time period really matters. Do we assume that those are different movement should have the same period of time between different symbol point? Is that implicitly met in the in this work?
In the data set that I use in the experiments, yes, they were synchronized and they had the same rate. But our assumption is that if they don't have the same rate, we can just simply go with the one that has the longest period between its points and convert all the other trajectories to that. So we are going to lose some data probably doing that, but it works.
Yeah. Another question is regarding to missing point, because the recording of a trajectory, I know that you are using video, but a lot of, to extend the applicability of your work, it could be applied to other kind of trajectory data, right? And using GPS, we understand that missing data during the data collection is one of the issues. Will that affect the robustness of your algorithm?
The second movement pattern mining approach that we had to call gapped movement mining, basically that one allows missing points. So it says, okay, I cannot see a few points in the middle. I can just skip that for both trajectories or for all the trajectories that I'm looking at. I assume I just skip the middle part and see if the beginning and the end are the same or not.
Okay. Okay. Yeah. Thank you very much for your answer. Yeah. Okay. If there's no other questions, let's move on to the next presentation. Thanks for the nice talk by Shihab. So the next presentation is on self-paced ensemble for highly imbalanced massive data classification. The presenter is Zinin Liu. He is a first-year graduate student at the School of Artificial Intelligence at Jilin University. His research interests mainly include the imbalanced learning and applied machine learning. So let's start the video.
Good afternoon, everyone. I'm Zhining Liu from the School of Artificial Intelligence at Jilin University. I'm here to introduce our work titled Self-Paced Ensemble or Highly Imbalanced Massive Data Classification. Let's start with challenges and motivations. With the development of information systems, it has become easier to obtain data, which has also brought us more large-scale, extremely imbalanced, and low-quality datasets. Such problem occurs in many areas, such as click-through rate prediction, fraud detection, and medical diagnosis. For an example that we encountered in practice, the task is to predict the claim probability of waybill orders. It has more than 3 billion samples, an extremely high imbalance ratio of 3,000 to 1. There are many sparse hierarchical features such as user IDs. Moreover, the data is provided by the users from mobile applications, thus containing lots of missing values and noises. Such tasks pose new challenges to learning systems. Existing imbalanced learning solutions can be generally divided into 3 groups. Resampling methods directly modify the dataset to rebalance the class distribution. Reweighting methods instead alleviate the bias by assigning higher weights to the minority samples or hard examples. Finally, ensemble learning frameworks can also be used to improve the above solutions, but none of these solutions can well handle our problem. Start with resampling. Although random resampling is easy to apply, it has poor performance that cannot meet actual requirements. The commonly used resampling methods, such as SMOT, perform resampling based on additional information by considering the neighborhood or clustering relationship between data samples. But additional information comes with the cost of additional computation. Finding nearest neighbors or clustering can be very slow on large-scale datasets. Besides, such distance-based solutions do not work well when the dataset is highly imbalanced or contains many missing values. Moreover, the oversampling methods even further enlarge the training set, which also brings more training cost. As for reweighting, cost-sensitive learning requires the user to have sufficient domain knowledge to set an appropriate cost matrix. Otherwise, it cannot guarantee a reasonable performance. Hard example mining methods such as AdaBoost and focal loss are known to be sensitive to noises and outliers. Finally, ensemble methods usually have better performance. For example, one can use bagging to lower the variance introduced by undersampling. But the problems we mentioned before still hold in their ensemble versions. Given the above discussion, our goal is to design a practical learning framework that can effectively handle large-scale data with extreme class balance while being robust to missing values, noises, and outliers. That motivates us to propose the self-paced ensemble framework. In response to those challenges, our method has 3 key features. First, we use undersampling to reduce the amount of data required for training. Second, we introduce the concept of classification hardness to achieve adaptive resampling without relying on computing the distance between data samples. Third, through a self-paced learning scheme with Hardness Harmonization, our method guarantees a fast convergence speed while being robust to the outliers. This is an overview of our method. In each iteration, self-paced Ensemble selects the best training subset and use it to train a new base classifier, then add it into the Ensemble. In the red box is a core component of our method, Hardness Harmonization undersampling. Before we describe the practical algorithms, we first demonstrate the concept of classification hardness and its advantages in imbalanced learning. First, we must note that the class imbalance is not the sole source of learning difficulties. There are other important factors also plays important roles, such as the small distance problem, presence of noises, outliers, and class overlapping. We introduce classification hardness distribution to integrate all these factors into our learning framework. So what is classification hardness? Intuitively, it reflects how hard is the sample to be correctly classified by the current model. It can be given by any decomposable error function that can be calculated on a single data example, such as absolute error, squared error, and cross entropy. Here's an example of using absolute error to calculate the classification hardness. There are two key advantages of considering hardness distribution in imbalanced learning. First, it fills the gap between imbalance ratio and the actual difficulty of the learning task. Consider the examples given in figure A and D. There are 3 different datasets in each figure with imbalance ratio of 1 to 1, 1 to 10, and 1 to 100. The only difference is that the distribution is separable in figure A, but overlapped in figure D. So, despite having the same imbalance ratio, the task in figure D is actually more difficult. In this case, imbalance ratio cannot reflect the difference between the 2 tasks. But if we consider the classification hardness, we find that as the imbalance ratio grows, the hardness also grows in the overlapped task, but stay constant in the non-overlapped one. That enables us to identify how hard a task actually is. You may also notice that even on the same task, the hardness distribution is quite different when we use different classifiers, as shown in figure E and figure F. That is because different learning models have very different capacities, and hardness distribution can capture such difference that is ignored by other pre-processing methods such as smooth. According to the classification hardness, we can generally distinguish 3 kinds of samples: trivial, noise, and borderline samples. The trivial samples were indicated by those blue points. They have tiny hardness values, but due to their large population, the total hardness contribution of trivial samples is non-negligible. As trivial samples are already well classified by the current model, they cannot provide new information for future training. Therefore, we want to reduce their population and leaving only a small part of them to represent the skeleton of their corresponding distribution. The noise samples are represented by those dark red points. Their number is relatively small, but each contributes a large hardness value. As we all know, noises can disturb the model training, so it's necessary to reduce their negative effect. Finally, the borderline samples are indicated by those light red points. As you can see, they are close to the decision boundary, thus have higher information entropy, and that makes them more informative for further mining. Therefore, we hope to emphasize the importance of borderline samples. Now, although we have those guidelines for manipulating different kinds of data, in practice, it is usually difficult to clearly distinguish the above three kinds of samples. So instead, we identify data samples under finer granularity by cutting them into several bins according to their hardness values. That gives us a hardness histogram. It approximates a distribution of hardness values and implicitly reflects the task difficulty. Here is an example. The left part shows the number of samples in each bin, and the right is the summation of the hardness values in each bin. Now we come to the practical algorithms. Our first algorithm is hardness harmonization. Specifically, we perform resampling to equalize the hardness contribution, which is the summation of hardness values from each bin in the histogram. By doing that, we can obtain a harmonized subset. As mentioned above, we are doing this to increase the weight of borderline samples while reducing the effect of trivial and noise samples, so as to obtain a better performance. But hardness harmonization has a problem. As the training progresses, the number of trivial samples grows fast. Simple harmonization will still leave lots of trivial samples, and that will slow down the model from obtaining new information. Therefore, we propose a second algorithm to improve it. Specifically, we introduce a self-paced factor alpha. It's a penalty factor to reduce the weight of large bins in hardness harmonization. The larger alpha is, the more we focus on harder samples, but know that we always retain a reasonable proportion of trivial samples to prevent the negative impact of noises in model training. Now we can control the undersampling with a self-paced factor. As shown in the figure, alpha grows during the training, so we focus more on harder samples in later iterations. Now we can summarize the SPE framework. You can check the details in the paper. Know that in line 7, we use the tangent function to control the growth rate of the self-paced factor alpha. Finally is the experimental results. We carry out experiments on a synthetic dataset and 5 real datasets. Know that all the real datasets we use have large sizes and high imbalance ratios. In order to comprehensively evaluate the performance, we use a total of 4 different criteria and 9 different classifiers. We compare SPE with 19 baselines in terms of performance, efficiency, and robustness. First is the performance on a synthetic dataset. Know that we use 8 different base learners, and SPE performs significantly better than other methods in all cases. SPE also outperforms other baselines in real tasks under different settings using different base learners. We also compared SPE with certain traditional resampling baselines. We can see that SPE achieved the best performance using only 6,000 of training samples with 1 second of resampling time. Other distance-based resampling methods, despite using far more training data and computation to perform resampling, still demonstrate unsatisfactory performance. Then we compare SPE with other ensemble methods. Again, SPE has a significant performance improvement compared to other undersampling-based methods that use the same amount of training data. While comparing with oversampling-based ones, SPE uses only about 1/300 of the training data, but achieve even better performance. This visualization of different methods can help you understand the differences between them. As you can see, our method works best in restoring the underlying data distribution. Finally, we test the robustness of various methods under different levels of noises, class overlapping, and missing values. Experimental results show that SPE is robust to lead factors, and it can achieve a reasonable performance even under extreme cases. And that's all. We open sourced the code on GitHub. Please check the link down below and try it out. Thanks for your interest in our work, and have a nice day.
Okay, great. Thanks, Zinin, for the very nice presentation. Is there any questions for this talk? I do not see any questions from the chat board. If not, I have a question. With the recent development in deep learning, actually there are a lot of very well-known classifier being developed using the neural network models. I know that you have tested a lot of those classifiers, but I don't see those deep learning models being tested. I wonder whether the idea, I expect that the issues still exist in using those deep learning models, but I wonder whether you have tried it, have a test on some deep learning classifier models. If you have, can you share your insights with us?
Okay. Thank you. Can you hear me?
Yes.
Okay. That's a very good question. And we actually tried out using deep learning methods with our resampling framework. And we use deep factor machines to make it, and to make an example with gradient boosting machines in the application inside Microsoft, which is the task I mentioned in the first place, to predict the probability of Weibull order if it will be claimed. And yes, we do not include deep learning methods because it's already many methods that aims to tackle this problem by modifying the loss functions. And our method mainly focus on resampling, which makes it a more generic framework that can be used for many base classifiers. And as you know, for many deep learning methods works well with computer vision and neural and NLP tasks. But we are dealing with tabular data, and deep learning methods generally works worse than traditional methods.
Okay, great. Thanks for.
We tried deep factor machines and it works, but we do not have further experiments.
Okay. Yeah. Thank you very much. Yeah, there was a loss of the signal for a few seconds. Yeah.
Yeah, my network sometimes stoppy. So if anyone has more questions, please email me or in the future. So sorry for my network, and thank you.
Sure. Okay. Yeah. Let me thank Zinin again for the nice presentation. So let's move on to the third paper. The third paper is on SAN, Scale-Space Attention Network. The speaker is Yash Garg. Yash is a PhD candidate from Arizona State University. His research involved extracting key insights from the data and use them during model training process. So let's welcome Yash. Yes, this is the paper. Please go ahead.
I want to thank everyone for attending my presentation, Scale Space Attention Network. This work has been done in collaboration with researchers at Arizona State University and University of Torino, Italy. I want to acknowledge various NSF grants that have made this work possible. Technological advancements have enabled availability of large number of data such as images, videos, and time series. Such availability has allowed for advanced analytical tasks such as noise elimination, dimensionality reduction, and classification. A solution that has proven great success in a variety of applications is neural networks. Here, the goal is to learn a mapping function f that maps the input x to the output y using a trainable model hyperparameter, such as theta. Neural networks can be seen as a sequential arrangement of computational units organized as layers, where there could be various types of layer: input layer, output layer, hidden layers, and pooling layer. For the purposes of this paper, we focus on hidden layer being a convolutional layer. Here, each layer can be seen as a combination of linear and non-linear operation where the output of one layer feeds into another. It is also interesting to note that convolutional layers can be seen as a layer that learns features at different scale, where the size of the scale is driven by the kernel size. And the scale size can effectively double with every downsampling, such as pooling operation, relative to the input size. While neural networks have proven great success, they have challenges of their own. Real-world data necessitates large and complex networks, which leads to millions of parameters being learned. Consequently, learning these millions of parameters simultaneously can make the network vulnerable to noise and overfitting. Often, these parameters and the intermediate data they generate are not of equal importance. So one really wonders what can be done. These challenges allows for exploration of new opportunities. One intelligent way is to learn the importance of individual parameters and the intermediate data in form of attention mask, thus allowing us to understand the cause and effect analogy here. One way to formalize this problem is through incorporation of attention mask matrix MA, which encodes the importance of individual intermediate data at any given layer along with the network parameters. In order to learn the importance of intermediate data in a neural network, the conventional way is to connect an attention block in parallel to every trainable layer in the network. The attention module relies on the fundamental of autoencoder, where the encoder module feeds on the intermediate data Y and learn a reduced representation C. The decoder module then tries to reproduce the original intermediate data from the reduced representation. The crux of this process is to learn an intelligent autoencoder that is able to reproduce the original data with minimal loss, thus highlighting the richness of the data, that is, its importance. While autoencoder-based attention modules have shown great promise and success, they suffer from key fundamental problems. First being the size of the hidden data, that is, the size of reduced representation. We argue that an insufficiently small data can lead to overcompression of the information, making it difficult for decoder module to reproduce the data, thus reducing the efficacy of the attention module. Another aspect is the lack of domain knowledge in these attention modules. That is, they primarily rely on the network's learning process rather than self-capabilities. One aspect that has been overlooked but we highlight is the lack of cross-layer information. It is known that neural networks are sequential layer networks where each layer feeds on the prior layer. That is, we can extract some information by using a combination of layers, which is missed in these cases. Various works have been done in this domain to inform the attention module of various knowledge that exists in a network, particularly for images. We explore two key of those such works, such as CBAM and BAM. Given an input with spatial and channel information, where spatial information represents the size of the image and channel information represents the number of nodes or features of the layer. Both of these work aim to attend the channel information and the spatial information separately. CBAM proposes to do this attention in a sequential fashion, that is, first they attend the channel information followed by a spatial information, whereas BAM does this in parallel, that is, it does both of these attentions simultaneously and merges them in the end. However, we observe that these two methods suffer from overgeneralization of the data through the use to the significant use of averaging and maximization operation, and they again rely on single layer. We propose a novel two-layer driven attention model which aims to identify salient region to focus on through comparative analysis of the adjacent layer outputs. The key motivation lies here is to identify local changes in the immediate feature outputs and translate them into attention region. Let's dive into detail. SAN focuses on two adjacent layers in the feature branch that are represented by the blue box. Given these outputs of the two layers, SAN aims at learning the attention mask, that is, the matrix MA, through a two-step process. First step being salient change extraction, followed by learning an attention region through translation of salient changes into region. In order to extract salient changes, we propose a difference of convolution operation that takes the difference of two of these layers output, that is, the output of the convolution layer. However, there is a limitation here. The two outputs are not represented on the same basis vector, as both layers contain their own mutually exclusive set of convolutional kernels. Therefore, we propose a channel averaging operation where the output of previous layer, that is y-1, with this operation, we are able to preserve the spatial information while summarizing the channel information. In order to compute DOC, that is difference of convolution, the shape of the output of the two layers must be aligned, both logically and semantically. Therefore, we propose to stack the average channel information in the previous layer, denoted by y bar L-1, to align the shape of the previous layer output with the current layer output. With this stacking operation, both the outputs are now aligned both logically and semantically. Hence, we can extract salient changes. We argued that these salient changes in the latent features is the location for the network to focus on. Therefore, we proposed a difference of two convolution outputs represented by delta y. It is important to note that we propose to take the absolute difference as we are interested in the change, not the direction of the change. Intuitively, we want to prevent the gradients from cancelling each other out, and unsigned difference is used. Another aspect is the introduction of additional convexity in the network. It is important to note that networks work with real valued data. Therefore, even a tiniest change will be detected by the DOC operation. Intuitively, these tiniest changes can contribute to noisy information in the network, thus negatively impacting the model performance. Therefore, we propose a weighted augmentation of the salient changes to highlight the relevant and suppress the irrelevant one. In particular, we propose a neighborhood comparison operator to determine if a salient change is relevant or not. We create a 3x3 pixel neighborhood around a change of interest, therefore leading to 8 neighbors excluding itself. Then we determine how many of these neighbors are smaller than the current change of interest, thus leading to our weight. Therefore, a larger weight value signifies more importance of the current change and smaller signifies less importance. We further observe that one might think, why not just use a hard extrema, that is, weight be either 0 or 1. We argued that this will lead to a significant sparsity of the network, again significantly impacting the model performance. Following the extraction and augmentation of the salient changes, our final step is to translate this salient extrema into salient region. While the DOC extracts salient changes, the augmentation steps introduces some aberration that can limit the model performance. Therefore, we propose a smoothing operation that translates this augmented changes into smooth regions through the introduction of an additional convolutional layer in the attention block. The smoothed output is a domain-aware attention mark that is learned by leveraging two-layer outputs. Therefore, a two-phase process involving salient change extraction and translation of salient changes into salient regions. Next question is, how do we integrate the salient attention block into the network? A network can be seen as an architecture of interleaved trainable and pooling layers. Given these two types of layer, we define two attention positions. First, the bottleneck position. we define bottleneck as a position in the network right before the pooling layer. And another position we define is full attention. That is, we put attention block after every trainable layer in the network. Next, we present the experimental evaluation of SAN, where we considered various scenarios. In particular, we present results for 3 key benchmark architectures, which is LeNet, VGG, and residual networks, followed by 11 benchmark dataset ranging from MNIST and Fashion MNIST, which represents environment constrained datasets of handwritten digits and APRILs. For real-world dataset, we considered CFAR family dataset, German traffic sign recognition dataset, and ImageNet dataset. We considered CBAM and BAM network architectures. In the interest of time, we present results for VGG, German traffic sign, and ImageNet dataset for the 2 state-of-the-art architectures. In this result, we present the model performance of the proposed attention module over GTSRB dataset, that is German traffic sign dataset, and we can clearly see that the proposed attention block is able to outperform the state-of-the-art architectures with a significant margin. Next, we also present the result from ImageNet dataset, which is a very complex dataset with large number of images ranging in a million. Here we can see that we are still able to outperform the state-of-the-art architectures both in bottleneck and full attention position. Now, you might be wondering why this is the case, why SAN is able to outperform. Though we discussed the key intuition of SAN attention block in the prior slide, here we present the intermediate result of the network that shows that SAN is able to learn more diverse and fine-grained attention marks in comparison to CBAM, which learns fine-grained attention but lacks diversity, which may not be relevant to different kernels or channels present in a given layer. Whereas BAM is able to learn diverse attention marks, but we argue that it does not contain fine-grained information which is necessary to actually identify the patterns contained in the images. Therefore, we summarize that conventional attention blocks lack domain knowledge and cross-layer information, thus leading to limited performance gain. With the proposed attention block architecture, we leverage a novel difference of convolution operation where through difference we are able to identify the salient changes, and through convolution we are able to identify local features. And the extrema weighing and smoothing translate these changes into informed attention regions. Thank you.
Okay. Any questions from the audience? Okay, I have a question. So Yash is here, right? So I have a question about the use scenario of the proposed attention. Conventionally, the attention mechanism has been proposed and used for sequence-to-sequence kind of application. Here, I think what you propose here is target on different kind of application scenario and focusing on convolution and pulling layers. Can you share some insights, comparing to conceptually and technically, comparing to what you propose and those are conventional attentional mechanism for like RNN?
Yes, so what we do is we work with the output of the layer. So in case of RNN, we have also extended this work and presented results in the paper for recurrent networks as well. So once the RNN layer finishes its computation and all the state results and the entire sequence is returned, we apply this attention block on RNN outputs as well, which instead of integrating it into the RNN block, we use this attention block as a post-processing unit to the RNN outputs so that we can apply this information on recurrent networks as well.
Okay.
So conventional work on a timestamp basis. Given a timestamp, they apply attention either across the timestamp unit for different features. But CBAM lets the recurrent unit or recurrent layer finish its computation and then applies attention as a post-processing, more fine-grained or coarser attention module.
Okay, and what is the problem if you simply adopt those attention mechanism, used for INN and under the architecture, the model scenario that you are considering?
Sorry, can you repeat the question? I couldn't hear because of connectivity.
Okay, yeah, my question is that can those INN attention mechanism be used in the scenario that you are considering?
We can. But the key question here is, what's the meaning of the salient changes in the existing attention modules?
Okay.
They focus on just working with the layer output and using their magnitudes as the driving mechanism for the attention. But what we focus is on how the network is evolving between two layers, how network is changing. So if we can integrate the salient change extraction concept into those attention modules, then yes, we can extend the existing RNN-based attention mechanisms to use our style of attention.
Okay, thank you very much. So they are conceptual difference between them.
Yes.
Yeah, okay, wonderful. I think for the sake of the time, let's move on to the next presentation. And thanks, Yash. The next paper is on a novel approach to learn consensus and complementary information for multi-view data clustering. The speaker is Dr. Kong Long. She received a PhD degree in computer science from Queensland University of Technology in Australia, where she is currently working as a postdoc. Her research interests include data mining and machine learning techniques for multi-view data learning. So please start the video.
Hello everyone, my name is Han Leung and I am presenting the paper titled A Novel Approach to Learning the Consensus and Complementary Information for Multi-View Data Clustering. This is the outline of the presentation. We will have introduction, related works, the proposed 2CMV method, conclusion, and future work. Multi-view data is the data where data samples are collected from multiple sources or represented by multiple types of features. Examples are shown in the figure below. The multi-view data clustering is the process to simultaneously clustering all view data to learn the accurate clustering solution. The multi-view data is deemed to contain the consensus and complementary information. The consensus information is how different data views embed a compatible latent structure within the data. The complementary information is how each view providing a diverse characteristic within the data. For example, in the multi-source news dataset, all data sources share common information, which is the consensus information, but each data source presents some distinct information, which is the complementary information. So the challenge of multi-view data clustering is to ensure learning both consensus and complementary information to help achieving the accurate clustering solution. Since the aim of the method is to propose, the aim of the paper is to propose a method. The aim of the paper is to propose a method that can correctly learn the consensus and complementary information from multi-view data. We first investigate how existing methods deal with learning the consensus and complementary information. Learning the view shared and or view specific information is a long-standing goal in multi-view data. Many works focus on learning consistency or diversity only. Most methods learn the consensus information. For example, multi-view non-negative matrix factorization learns the consensus information by embedding the most common latent features from all views. Multi-view spectral clustering by common agent vectors learns the consensus information by learning the common largest agent vectors from multiple views. Multi-view coupled matrix factorization learns the consensus information by learning the common representation shared in multiple views using coupled matrix factorization. Only a handful of methods learn the complementary information. For example, diverse non-negative matrix factorization uses a simple diversity constraint on low-rank representation of different views. Some subspace-based methods use the complex constraint HSIC to identify the distinct features in subspace. However, these methods fail to ensure that enough consensus information has been learned for the multi-view learning. Few methods learn both the consensus and complementary information. For example, distinction-based consensus spectral clustering assumes that there are two components in the new representation, which are the consensus component and the complementary component. It uses HSIC constraint to enhance the diverse information learned from different views. However, it is a spectral-based method. Therefore, it is ineffective on high-dimensional and large-scale datasets. Consistent and specific multi-view subspace clustering is a subspace learning-based method. It also assumes there are two components in the new representation. However, it uses simple nuclear norm for the consensus component and the L2 norm for the complementary component. Partially shared latent factor is a non-negative matrix factorization-based method on multi-view data designed to learn both information. However, it uses label information. In summary, a matrix factorization framework can effectively learn the low-rank representation for high-dimensional and sparse multi-view data. However, there is no matrix factorization framework that can learn enough two types of information for multi-view data. Manifold learning technique is to learn and preserve the local geometric structure when mapping data from high to low dimensional space. It is combined with matrix factorization framework to learn the low-rank representation that maintains the original local geometric structure. In multi-view data, there are two main ways the manifold learning is applied. The first way is to learn the manifold on each view data and allows the low-rank representation on each view to be smooth with the view's manifold. And this will help learning the good view-specific information. However, it ignores the correlation among different views manifold. The second way is to learn the consensus manifold, which is the manifold that contains all manifolds of all views. It incorporates the associative relation among views and allows the consensus low-rank representation to be smooth with the consensus manifold, therefore can help learning more insightful low-rank representation. However, learning the correct and useful consensus manifold is a non-trivial task. Therefore, learning a useful manifold for multi-view data learning is needed for a multi-view learning method. So we propose to learn the optimal manifold incorporated in a factorization-based framework to simultaneously learn the consensus and complementary information. Before we go into detail of the proposed method, let's have a look at the multi-view data definition. We are given a multi-view data with NV views. SV is the data on view V. We would like to learn HV and WV, which are the low rank or low dimensional representation and basic representation on data in view V. The goal of multi-view data learning is to learn the most common low dimensional representation denoted as Histar. This is the objective function of the proposed method. As the first contribution, we proposed a two-component model, as illustrated in the figure and formulated in the first term of the objective function. We can see from the figure that both couple matrix factorization framework and non-negative matrix factorization framework are utilized to factorize the multi-view input data. The non-negative matrix factorization framework will learn each low-rank representation on each view V, which is HV. And this new low-rank representation HV on different views will be used to create HCOM, which is the complementary component. Simultaneously, couple matrix factorization framework will be used to learn the consensus component, which is Histar. The final low-rank representation will be the combination of both components, as given in the figure B. As a second contribution, we propose to learn the optimal manifold, which is the most consensus manifold. As you can see in the figure, the optimal manifold is the intersection part of all manifolds of all views. The optimal manifold is calculated from the optimal affinity matrix A-op, which is calculated by taking the minimum affinity values from all views. Learning and preserving the optimal manifold is formulated as in the second term of the objective function, and it is to ensure that all data points residing close in all views in the original space will be preserved to remain close in the new map space. For the third contribution, we proposed a complementary enhancing term, which is based on the concept of orthogonal constraint. The benefit here is that imposing the orthogonal constraint on the two components of the model will help promoting the independence or complementary information for the two components. Then we have the final objective function, which includes three terms. The first term is to learn the two-component model. The second term is to learn and preserve the novel optimal manifold. The third term is to enhance the complementary information while projecting data to lower dimensional space. We also make use two trade-off parameters for the manifold learning and for the complementary enhancing term. In the experiment, we use a wide range of image and text dataset to evaluate the performance of the proposed method and other benchmarking method. The characteristic of benchmarking methods are given in the table below. We can see that regarding to the adopted framework, MVCMF is the only method that uses couple matrix factorization model. Other methods using non-negative matrix factorization, while 2CMV using both NMF and CMF. Regarding to the type of manifold learning, LPDMMF learn each view manifold. MM and MF learn the consensus manifold, while 2CMV learn the optimal manifold. Regarding to the complementary information, D and MF and LP, D and MF is the complementary information is enhanced among pairs of views, while in 2CMV, the complementary information is enhanced between two components. We also make use two versions of 2CMV, 2CMV-OM, which is the 2CMV with the optimal manifold learning only, and 2CMV-CE, which is the 2CMV with the complementary enhancing term only. The experiment, the clustering results are given in the two tables. As you can see, 2CMV and its variation easily outperform other benchmarking methods demonstrated by higher NMI and accuracy on all datasets. It's also interesting to note that 2CMV outperform its variants, which are 2CMV CE and 2CMV OM, which is an evidence that using both optimal manifold and complementary enhancing term are important so that we can learn a good performance for clustering multi-view data. Furthermore, we can see that LP, D, and MF, which learn the manifold on each view data, and MM and MF, which learn the consensus manifold, are easily outperformed by 2CMV OM, which is our method which only use the optimal manifold. So this is the evidence to show that learning the optimal manifold is effective and useful, so that we can learn a better clustering solution. We also conduct separate experiments to investigate the performance of the proposed method and other benchmarking method with the alteration of parameters. The two figures on dataset D1 and D5 illustrates that the proposed method easily outperforms other benchmarking methods on a wide range of parameter selection. In conclusion, we have proposed a novel integrated factorization-based two-component model, which is to learn the consensus and complementary information using couple matrix factorization and non-negative matrix factorization. The optimal manifold and complementary enhancing term are proposed and incorporated to learn useful consensus and complementary information for multi-view data. In future works, we will analyze the update rule to investigate the effect of different components of the model to the final representation. We will integrate clustering identification with the low-rank representation into the objective function to build a unified one-step process of multi-view clustering. Thank you so much for listening.
Very nice presentation. Thank you. Is there a question for the speaker? Okay. I intend to keep the session ended on time, and I look at the schedule. It looks like we are behind the schedule right now. So I will skip the questions and move on to the last presentation. The fifth paper is on summarizing hierarchical multidimensional data. The speaker is Professor Lattice. Lattice is a professor of computer science at the University of British Columbia, where he direct research on data management, data mining, machine learning, fact-checking, misinformation management, and mitigations. Please start the video.
Hey everyone, I would like to tell you about the research we've done on constructing optimal hierarchical summaries over multidimensional data sets. This is joint work with Alex Kim and Devesh Srivastava. Alex recently graduated from UBC and Devesh is from AT&T Research. Increasingly, we find that data sets that tend to be used in decision support and other data-driven applications tend to be larger and larger in size, and they often come with multiple dimensions. In these applications, a good understanding of the data set can benefit from repeated applications of exploration and summarization. And given that the data set is multidimensional, we would like to try and exploit the associated dimension hierarchies in constructing optimal summaries. There is a great variety of different possible summaries exist, depending on whether one is looking for lossy or lossless summaries, and depending on the structure and constraints that we want the summary objects to satisfy. Let me quickly highlight three key pieces of related work. Many years ago, in their KDD paper, Agrawal and company, they proposed an elegant polynomial time algorithm for constructing optimal lossless and lossy summaries, but this work is confined to one-dimensional data. Subsequently, well, not subsequently, but independently, Karloff and company, they were looking at multidimensional data. The kind of summaries they were interested in constructing correspond to hyperrectangles constrained by dimension hierarchies, but these rectangles are allowed to overlap arbitrarily. So in their framework, unfortunately, even in 2 dimensions, the optimal summary is NP hard to find, so the authors propose a randomized 2 approximation algorithm, and they confine themselves to just lossless summaries. In multiple dimensions, Ruhl et al. In their Sigmod paper from a number of years ago solved this following problem. Given a summary size budget, K, find a summary whose size is under budget, satisfying some interesting properties, okay? Now, their algorithm finds the optimal solution for 2 dimensions, but for higher dimensions, they provide an approximation algorithm. In all cases, regardless of the size budget, the algorithm does not come with any worst case error, okay? That's important to bear in mind. Given this context, we are interested in summaries that are concise, can be efficiently computed for any number of dimensions, and gracefully extend themselves from the lossless case to the lossy case, and they always provide worst case accuracy guarantees. Okay, this is what we are looking for. To understand the space in which we look for optimal summaries, we just consider the cross product of the dimension hierarchies. So that naturally defines a lattice. As a quick example, consider an outdoor equipment store with 2 dimensions, product and store locations. The cross product of these 2 defines a lattice. What I'm doing here is show the lattice not as a conventional lattice diagram, but more like a 2-dimensional data warehouse kind of grid. The values that you see in each cell, you can think of that as the ratio of monthly sales between 2 successive months for each of these cells. Okay. All right. I would like to quickly socialize the 3 summaries that we're looking for. So for that same toy data warehouse example, the summary here should be read as follows. For the topmost region corresponding to all stores and all products, the default value is 1, which means that by default, all cells covered by this region should have a value 1. Whereas its child region, yellow, says that for these 3 cells, the value is 1.2. It overrides the value that was inherited from the parent. And the same thing is done recursively for its child region, which consists of a single cell. It has a value of 0.8, which overrides it. So this is the way the summary is meant to be read. So to construct these summaries, we need to look at a slightly extended lattice structure in order to accomplish a certain task. It will become clear shortly. So starting from the root of the lattice, we pick exactly one of the dimensions. And whenever you are at a dimension node, you choose all its lattice children, and for each lattice child, you repeat the process. You pick exactly one dimension child, and from there you pick all its children. You do this for every single lattice node that you are at until you have exhausted, completely covered the lattice, and this will have described for you an embedded tree. Now, in this embedded tree, we actually don't have any use for these dimension nodes. They were just a means to an end, so we can throw them away by doing an edge contraction. For example, getting rid of this node and making these two nodes immediate children of the camping equipment all stores node. Okay. Doing so results in the following full embedded tree structure, which again, I'm showing you in part. So then the tree summary is defined as follows. Tree summary is obtained from a full embedded tree along with a weight assignment scheme, which supplies weights for a subset of the nodes. Then what you do is get rid of the nodes that don't have weights and connect all remaining ancestor-descendant pairs in general directly with a parent-child edge. Okay, so let me quickly illustrate that again. So these are the weighted nodes in this full embedded tree, which is again being shown in part for space reasons. Now let's highlight the weighted nodes. Now throwing away unweighted nodes and doing that sort of parent-child connection leads to the structure. And this is the corresponding summary embedded tree. And this is, by the way, the corresponding summary rendered in 2D grid structure that you saw a few moments ago. All right, so formally a tree summary is then a triple. The first component is the full embedded tree from which the tree summary is meant to be constructed. A weight assignment scheme, which as I said before, is a partial function which assigns weights to a subset of nodes of T. And T sigma is induced by the weighted nodes that are defined by W sigma. Okay. Now, all of this is only good provided it does work for us in the sense of allowing us to recover the values of the cells in the data warehouse. So that's formalized here. So we have such a structure such that for every cell, its value exactly matches the weight of the closest ancestor in the summary embedded tree. Okay, so the match condition has to be obeyed. Now, if you were interested in lossy summaries, all we need to do is replace this match condition by saying for every cell, the value, rather the weight of the closest ancestor for that cell, that value should lie between the true value of the cell times 1 minus alpha to true value of the cell times 1 plus alpha. It should lie in this loss interval. As long as the closest ancestor's weight lies in this loss interval, we are good. Okay, with this one change, we're able to handle both lossy and lossless summaries. The formal problem statement then is given a multidimensional data set with a corresponding lattice structure which comes from the dimension hierarchies and a loss parameter alpha. Find an alpha approximate tree summary which has the smallest possible size. Okay. Now, the key technical property that enables us to design an efficient algorithm for finding optimal summaries is what we call blocking lemma. Let me quickly illustrate that for you. Let's say that T prime is a subtree of some full embedded tree, and somehow magically I know how to find an optimal summary, optimal weight assignment within T prime. Now, suppose you give me an arbitrary weight assignment scheme for the entire FET, entire full embedded tree, where that's the tree that contains this T prime as a subtree. So if you give me, then here is something I can do. I can transform the weight assignment scheme that you gave me by getting rid of W here and editing that to W star. In other words, in all nodes of T prime, W star is what you listen to. You assign the weights according to W star and leave the weight assignment scheme alone otherwise. Now, if you do that, blocking lemma says that doing this transformation will not increase the size of the summary. Okay? This is key in constructing an efficient optimal summary. Quick overview of the algorithm. The algorithm makes use of annotations. Annotations will be decorated at every single lattice node. And annotation comes with 3 components: a value or weight, which essentially intuitively corresponds to the values that you initially got out of the lattice leaves or the cells of the warehouse, right? So that's their origin. And then there is a dimension node, which tells you which are the children of this dimension node that are meant to be covered by the summary value that you see here. and C says what will be the resulting size of the summary. That's the cost or size of the summary in a local manner. Okay, so then you propagate all these annotations up the lattice, favoring annotations bearing weights which are more popular among the set of siblings. Okay, you need to do this for every single dimension. And in the second step, from the root down, you repeatedly choose a drill down dimension which enjoys the least cost from among the various dimensions from that particular node. So you do this repeatedly. Whenever there are ties, they can be broken arbitrarily. So these two simple steps essentially constitute what the algorithm does in a nutshell. So it turns out that using the blocking lemma, we can show that this algorithm, which we call TS for tree summary, finds optimal summary in order of DHN time in the lossless case, where D is the number of dimensions, H is the number of levels in the lattice, N is the number of leaves in the lattice. And it can do so with a blow up of log N time in the case of lossy summaries. Okay. Experiments, I'm going to have to refer you to the paper for characteristics of the various data sets. There are several real and synthetic data sets in which we conducted the experiments. In terms of baselines, I'm not listing all the baselines here, but the key baselines are the ones that I described earlier in related work. The Karloff algorithm, which essentially is confined to two dimensions, and even in 2 dimensions, it's a randomized approximation algorithm. Okay, it doesn't consider a lossy case. And cascading analysts is the Sigmod 2018 algorithm. It has a bounded size, but does not come with any worst case error guarantees. TS is our algorithm. So in the experiments, obviously we measured the size of the summary, the error in reconstructing the value of the cells that you throw away from the summary while building the summary, and the running time of the summary construction algorithm. So the reconstruction error that we use is known as symmetric mean absolute percentage, which is basically the ratio of the absolute value, the difference between the original and the reconstructed value over the sum of the absolute values. Okay, and you take an average across all the cells. Okay, so this has the advantage of being bounded and easily interpretable. Quick look at some of the results. In the first set of experiments, we compare ourselves with the Karloff's algorithm, and very quickly the highlight is that Karloff's algorithm is faster than us. However, the summaries that come from that algorithm are less concise, and this despite the fact that they are looking at a space that is strictly richer than the space of summaries that we are looking at. In spite of that, their summary is less concise, which is kind of interesting. And because it only works for 2 dimensions, we stop the comparison with Karloff with 2 dimensions. For cascading analysts algorithm, so here is a subset of the experimental results. The first one shows how the worst case error performs with respect to increasing number of dimensions. So the key point to notice here is that with respect to average error, the 2 algorithms, cascading analysts and us, pretty much very close to each other. But with respect to worst case error, cascading analysts has a much worse worst case error. And this is the price it pays for not having a worst case guarantee. Okay. What about running time? Running time wise, again, surprisingly, cascading analyst is significantly slower than our algorithm. In fact, so much so that we couldn't run it on much larger data sets in our comparison. So the last set of experiments quickly shows that the TS algorithm scales reasonably well, both with respect to the number of leaves of the lattice, equivalently the number of cells in the data warehouse, and the number of dimensions. Okay, to quickly conclude, we looked at summarizing multidimensional data sets, leveraging dimension hierarchies that naturally come with them. Our proposed approach enjoys the fact that the summary is optimal for both an lossy and lossless case, and it can be constructed in polynomial time for any number of dimensions, unlike previous work that we looked at. In all cases, in our comparisons, we find that our summaries are more concise or can be obtained quicker or comes with better worst case performance. In future work, it would be interesting to consider summaries for multiple measures where each cell can have multiple measures, and find summaries which are robust against outliers. So we need to seek other means of approximating the cell values that are present in a data warehouse, some of which could be outliers. So I would like to conclude the talk here, and thank you very much for listening or viewing this video. I would be happy to take questions now.
Wang-Chen, you have to unmute yourself.
Yeah, thank you very much. It's really nice talk. I'm wondering whether the audience have any questions for last.
Can I ask you a question?
Sure.
So that's a very interesting topic. I think what kind of theoretical guarantees can you make for this kind of problems? Do you know doesn't it depend a lot on the kind of data? You know how good your approximation, the summaries, and can you say something about the quality of the kind of the data by how big the summary is?
Okay, so there are two different levels at which your question can, thanks for the question, very interesting question. There are two different interpretations of your question. One is literally, what is the theoretical guarantee? And the theoretical guarantee is that if you have a loss parameter, the parameter alpha that is supplied as input to the algorithm, the summary is guaranteed to be optimal relative to the loss parameter alpha. So that means the weight of every summarizing region, right, in the 2D grid that I showed for the illustration, the weight is guaranteed to lie within 1 minus alpha to 1 plus alpha of the true value of this cell, okay, recursively. So subject to that constraint, it is guaranteed to be optimal. And you saw the complexity, so it's an efficient algorithm. Now, I think a deeper interpretation of your question is, what can you say about the kind of sizes that you get in practice? And there, you are absolutely right. That just depends on the characteristics of the data. As a concrete example, right? So if you give me a raw data warehouse where every single value is different, and you are interested in zero loss, then I can't help you. You know, the algorithm will do its course, but it'll come back with a super large summary. So there has to be some level of regularity in the data. And in our experiments, especially on real data sets, we found that this sort of summary is particularly useful for summarizing changes in the data warehouse. So for example, consider two different snapshots, like what I said in the running example. For successive months, you look at the sales, or successive months, you look at some phenomenon. So while there may be considerable variation across cells for the raw values, in many real data sets, we find that the ratio of change tends to be within ballpark of each other. And if you, for reasonable loss tolerance, we are able to get concise summaries. So beyond that, I don't know how I would prove such a result theoretically. And if you have any ideas, I would be more than happy to hear.
So there are, I don't know how this would compare, but you know, sometimes if you can say there is a bound in the variation, I mean, how different can your neighbors be? Then from that you can derive some bounds on, you know, how much you need to. But I don't. Yeah, it's an interesting.
Yeah, that's quite intriguing. So yeah, requires careful analysis. Yeah. Well,
thank you.
Sorry.
Okay.
My video is. Yeah.
Okay, great. Thank you for the very insight, the insights. Okay, and also the question is really a nice one. I wonder whether audience have other questions. Okay, if not, then this concludes session 15. Once again, I would like to thank all the presenters for the very nice talk, and also thanks for all the audience for participating in this online conference. Okay, the next section will start at 2 p.m. Which is 3 p.m. Eastern time. Okay, so see you guys then.
Okay, great, thanks.
Thank you, good job. Thank you very much.
Yeah.
Bye, Lex.
Bye. Nice to see you.
Nice seeing you again.
Nice to see
Thanks
you
for coming.
guys. Yeah.